Thank you all for joining us for our very first session of Let's Make Glass, the Disordered Solid. My name is Jamaica Marshall, and I'm very pleased to serve as the Shadow the Scientist Programs
Rock
Manager.
on.
Now, today
Hang on.
you are, sorry, one second. Today you are in for a treat. We are here with Dr. Steve Feller, and subject matter experts are going to be the students at Coe College that work with him, and we're going to see them make a special type of glass. So let me take it right over to Dr. Steve to get us started. Steve, welcome.
Thank you, Jamaica. And hello, everybody. So with me, we have Brandon and Max. Can you see Brandon and Max behind me? Maybe you can.
Yes, we definitely can.
Oh, there
Hi,
they are.
Brandon. Hi, Max.
Hello.
And we have a few more people in adjoining lab who will do the making of the glass as well.
Oh, I
And
think we see some of them now. Steve, is that them? Yes.
it's them. And Brandon's in various waiting rooms all over the place here. Okay. So, hello, Rick, and hello, Bonnie. Is there anybody else? Maybe there
Rick,
is.
Bonnie, and Rob.
Okay, and Rob.
Yes.
Can you guys hear me all right?
Yes, we can hear you. I disabled the audio
Okay.
because we had some ambient noise, but they can post their questions and comments in the chat.
Okay, so we're gonna have Max over here check for the chat every so often, okay?
Mhm.
When a
And
question comes in, get my attention or get our attention, okay?
Mhm.
All right, so we got somebody monitoring the chat at all times.
Excellent. So thank you. Yes, Bonnie says we can hear you just fine in the chat. So everything in the chat first comes to me. It's just another security layer, and
Okay,
then I will repost it there for
okay.
everyone to see. Yes.
But Max,
And
meanwhile, we're
so
monitoring the chat, right, Max? All right.
thank you, Max.
So we are in Iowa. I'm not sure where Vonnie and Rob and Rick are, but we are in Cedar Rapids, Iowa, at Coe College. We are a small liberal arts college, but we've been making glass for well over 40 years anyway. So we're going to make some glass today and characterize it. We're going to do a thermal measurement of it as well. So let me tell you a little bit about what glass is. And of course, you could ask questions as you go along, especially with, not a huge group. You'll get quality time. So there's Rob. I take note he's in Los Angeles. Well, it's great to see you. And it's great that you joined us. And thank you, Rob. Oh, and we have Liz. We have another person. Um, I'm in Hilo, Hawaii, I take it. Okay, that's good. And if the others want to tell me, that'd be fine. But otherwise, I'm going to start off by defining what a glass is. Um, it's one of those materials that's a little hard to define, even though everybody, quote unquote, knows what it is. I mean, who doesn't know what glass is after all? It's in your windows, it's in your cars, it's on your phone. Glass is one of the most ancient, useful materials we have, and its uses now are exploding all over the world. It's an amazingly useful material. So a glass is a solid, even though sometimes you might know of what high school chemistry teachers sometimes say that it's a frozen liquid or something like that, mixed up and chaotic. No, it's a solid. Its bonds are as strong as any other solid, but it's screwed up. It's messed up. Does not form a regular pattern like a crystal. So there are two kinds of solids, crystals and glasses. And if you cool something quick enough, you can make a glass. We think out of anything, but there are practical limits. I mean, we can't cool something 50 billion degrees a second. We can do about 500,000 degrees a second and make a glass.
Close enough.
It's pretty fast. Um, so right now you see Chris, and maybe Chris can wave. There he goes. He can hear us. And there's Liz commenting. Yeah, the lab is interesting. You're looking at a lot of thermal equipment. All that stuff is thermal. By that, we're going to heat up a glass and see what happens to it. A glass is a screwed up solid, and when we heat it up, we're going to break the bonds that connect the atoms together, and we can see that in our measurement. That's going to be something like melting. Glasses don't melt because they're not crystals, but they soften like taffy. In fact, taffy is a glass, can be a glass. Okay, there we go from Rick. He's joining from Long Beach, California. And welcome, Rick. Okay. Oh, and so we have a new person, Lord, or Loud. I'm not sure how to pronounce the name. Welcome. All right. So, and Sam's coming on with another view of the glass lab, one of the glass labs we have at Coe College. We have many, but the students are getting ready to make the glass. Now that I see how this is working, we could actually stay in here and comment while the actual glass experiments take place live in front of you there. There's Zach has just moved into the forefront. He, he can wave, I suppose. There he goes. He's pretty photogenic there. And Chris behind them. They're getting psyched up and ready. So the glass we're going to make today, after some conversation, is a borate glass. Now, if you guys are in the Los Angeles area, some of you are, Long Beach and LA, if you go east of Los Angeles, you're going to come into the desert, the Mojave Desert. There's a little town there called Boron, California, a little itty bitty town that mines boric acid, the material that if you heat it will form a glass, and that's what we're going to use for the glass former. Most glasses use something else, silica, beach sand, but it's very hard to melt that in comparison to boric acid. When you heat boric acid up, you're going to get boron oxide, which is the glass, and water. Water's going to come out. And we're going to weigh the sample before and after and so on. Now, in order to make a slightly more interesting glass, we are going to take boric acid. I'm going to add sodium carbonate to that to make a sodium borate glass. This has very desirable properties. It's quite stable. See, these guys are getting into it. Move it a little closer to the camera.
Spreadsheet time?
Oh, it's spreadsheet time
I think it's
also.
spreadsheet time.
But if you look at Sam's, no, Sam's, stick with the bottle. Is that the boric acid, Sam?
So right now on screen, we see the spreadsheet.
Okay. So, yes. So if you look at Sam's, what do you call it? Camera.
Yeah.
If you look, you'll see a bottle of boric acid. Can you see that,
Yes,
Jamaica?
yes.
That's one of the starting materials we're going to use, boric acid. Maybe that was mined in Boron, California.
You can actually tell where it's from and what it has do thanks to the lot number. You can look
You
it up on
could go back to the company and find out. That's right.
you can look it up on their website.
But there's a good chance it was from Boron, California. 20 mule team borax and the old California miners, they were interested in that. So we used that. And the other bottle, if Sam can move it in, is there we go. This is good. Is sodium carbonate. That's going to make the glass have the right properties to melt and form for us. That's called the modifier. All right, now if we can go to Zach's spreadsheet, we'll just discuss that briefly. How we're going to make the glass. We're going to take, there we go. This is good, Zach. So what you can see there is a student-made spreadsheet that shows the starting materials as sodium carbonate. In fact, Zach can move the cursor to it. Sodium carbonate. There he goes, and boric acid. And he's already pre-calculated how much of each he needs to make material we know that makes a good glass. So the ratio of the two of sodium to sodium carbonate to boric acid is going to be 0.4. That's a good ratio based on our experience. And you can see we have a weight fraction of each. We're going to make right now that's set for a 6-gram batch, which will work. But just to show you how this, is versatile for us, can Zach make it an 8-gram batch? Will the numbers change? Boom, done. Now now we have an 8-gram batch. The weight fractions haven't changed, but the total is now 8 grams. We're going to take about 6 grams of boric acid and about 2 grams of sodium carbonate. And we're going to add them to a platinum crucible. Maybe Sam or Chris can. There we go. Get a little closer, Sam, to the camera. A little closer. There we go. So I can see the platinum crucible. Jamaica, can you see it all right?
Yes, I can see it, but it's not on the main screen. We still have the, but let me. We have screen sharing. Let me just change the spotlight
Also,
and add.
how versatile these are. If you do notice,
Okay.
these spreadsheets are very easy to copy. So if you're making multiple samples, you can copy one over, erase the experimental values, and make a glass with a slightly different composition. And so this is really helpful for us when we're making samples in a series where we're trying to study a specific property.
So you might wonder, why are we making these glasses? These are glasses that we want to do two things. We want to measure their physical properties, how dense they are, what the softening temperature is. Oh, there we go. Somebody's commenting. That's Jamaica.
Yes, that was just me, just welcoming everyone again and
Good.
telling them to put their questions and comments in the chat anytime.
And we have Max is checking that comment section. We will get to your comments within seconds of you sending it because Max is gonna let us know about that. All right, so the first glass will be an 8-gram batch, and you can see we need about 2 grams of sodium carbonate and about 6 grams of boric acid. We're going to lose water from the boric acid. Boric acid is boron oxide glass plus water. We're going to lose about 2.6 grams of it. Okay. And the mass of the glass will be what's left over, about 3.4 grams. And you'll be able to see this as we go along here. So what they're doing now is they're putting in the lot numbers so we know not only the company, but the actual batch of the materials in case we had a question, and the purity. These are very pure, they're in excess of 99% pure compounds. So that's been done now. And now we're actually going to weigh it out. We're going to weigh out about 6 grams, just shy of 6 grams.
The crucible's in.
So, oh, sorry. The crucible has been weighed at about 17 grams of platinum. It's about a half an ounce, by the way. That's worth about $600 in metal value today, just for the crucible, because we have to get it fabricated, double the charge. So the crucibles are over $1,000 each. We, of course, clean them and reuse them, as you might imagine. So we have the crucible weight in there because the compounds have to be weighed out in comparison to the crucible. All right, so Zach, are you weighing out the boric acid or the sodium carbonate?
We're weighing out the sodium carbonate.
So if you can get close to the camera there.
Can you unshare for a little bit?
Yeah, why don't you unshare? They'll fill in the chart.
Wow.
Oh, that's good. All right, so there's the compound. And my expert Zoom artist here is fixing everything on our side. That's Brandon. So what you can see now is Zach and Sam's the videographer there. Sam has a balance, and he's weighing out the sodium carbonate, and he's really good at this. He's done many of these glasses. So anyway, he's weighing it out. He has the blue gloves on there, and the crucible is on the balance. Sam, get close to the balance so they can see it. Thank you, Sam. There you go. There you go. Zoom right in there. Oh, that's good. So you can see the crucible's on the balance, and he's weighed out a little bit so far. Keep going, Zach. And Zach, because we want to move along, don't worry about me talking. Just do what you have to do. That's who he is. He's a very independent worker there. It's no problem. Meanwhile, Chris, what temperature's at the furnace are? We can walk over and take a look at the furnace while Zach is weighing out the compounds. So behind Chris are a couple of furnaces. And I started one off, I don't know, half hour ago or so. What's the temperature? I can't read it. Maybe you can zoom in, Sam. There you go. We're at 665 degrees on the way to 1,000. So that's Celsius. It's going to be almost 2,000 Fahrenheit in there. That's going to cause the reaction to take place between sodium carbonate and boric acid. The water is going to come out. It's going to bubble right out of there. And when we get it in the furnace, I'm going to show you that step actually. You can see the water coming out of steam. So meanwhile, it's getting hotter. Zach is weighing it out. So this will be a good time. Yeah, there you can see the lab. This would be a good time for Vonnie or Rob or Lord or whoever's out there. Feel free to ask a question now while Zach is continuing to weigh out the sample. It's going to take him maybe 5 or 10 minutes. That's all.
Well, I would like to start off with a question. You said that you all have been making glass at Coe College for like 50 years. How has the techniques evolved from when you first started to now? And have you been there the whole time, Steve?
I've been there. I've been here the whole time. My hair was black when I arrived. Now it's a lovely shade of gray, maybe. I don't know, white.
White.
It looks like a professor's hair now.
Mm-hmm.
And we have evolved. We had a furnace, and although the basic idea is the same, rapidly cooling a liquid to form a glass, we've added very rapid cooling, and we have developed maybe 5 or 6 different ways to make glass now. We can make it along a chemical route. We can mix chemicals together to form a glass without the heating, actually.
So we're not roller punching. We're not. We're plate punching.
Yeah, maybe Sam can walk over to the glove box that's in there. Or Chris can. There we go. There's the glove box. Sometimes we make samples in that. And that's to keep the samples dry. And if you look really closely, you can see one of our rapid cooling devices in there. There it is. You can see one of the rollers at the end. We have 2 rollers that are separated by about 1/1000th of a meter. Amount or so. Oh, we got a few more people joining us. And they're both named Max. So whatever reason, Max is well represented here.
Yep.
Okay, anyway, Zach, are you done with the sodium carbonate?
Yes.
And now you're doing the boric acid?
Yes, I've finished measuring out the sodium carbonate. I've moved on to the boric acid. So the only step I did in between was tear it out and then clean the spatula.
So when he says tear it out, he means he's going to set the balance back to 0. And then all he has to do is add the exact amount of boric acid he needs. Modern balances are good about that kind of thing. They're all digital now.
If you couldn't tell, Doc is a big fan of boron. Written a few books about it.
Boron is, what's nice about it is that it doesn't require a very high temperature. It might seem like a high temperature because it's like 2,000 degrees Fahrenheit, but that's easily achieved with a lab furnace. And we have a question. There we go. We have Vonnie. What is added to the elements to make glass bulletproof? Well, most bulletproof glass is made from silica, beach sand, very highly refined, pure beach sand. But basically, it's how the sample is cooled to make it bulletproof. If you put it under stress, it makes the glass much harder. And probably you've noticed, I think you've noticed that when a bullet is shot at bulletproof glass, it's a good question, by the way, Vani. It forms a a pattern of like spider web cracks. That's what happens as the stress is released from the glass. So because it's so hard, it's hard for the bullet to get through, but it can certainly break the glass. Bulletproof glass is breakable, but it's designed to have enough stress in it to not shatter even when a bullet hits it. So it's a silicate-based glass, probably some sodium carbonate in there. There's some sodium carbonate thrown in to lower the preparation temperature, and some other stuff as well. And then what they do is they'll dip the glass, like the window, into a liquid to stress it. Um, that's how you make like glass also for like hockey rinks, that super hard glass that when the players bang against it, if it does crack, it forms very tiny cracks, spiderweb like as well. Now we have Lord.
Also, we have a machine here to test the hardness of glasses.
We can measure the hardness and compare it to diamond. Diamond's the hardest of the solids. So there's a hardness scale. That our glasses don't tend to be very hard. We haven't really focused on bulletproof glass, but it's in our family of materials. Now, Lord is joining us from Africa, from Ghana. This is exciting. Hello, Lord. Thank you for this cool live stream, and thank you for joining us, Lord. I was curious about what desired properties you aim for when creating your glass, and how does that influence the various input factors? Well, that's a very good question. One of our instruments, which is not in the room they're in now, measures. We actually have two sets of instruments that measure how well they conduct electricity. So we're interested in making better batteries. We've worked with some companies on that and some colleagues. And the way batteries work, you maybe have heard of a lithium battery. The whole lithium atom moves in a glass if you apply a voltage across it. Voltage is a fancy name for electrical push. You want the battery to push the lithium atoms, which are typically charged atoms, through the glass. That's what you need in a battery. You got to get through that glass between the two electrodes. It's called an electrolyte. That's one use of it. Some of our glasses are very dense. Brandon maybe can comment on that because he's been working on that project.
Yeah, so for the glasses that I'm making, I'm trying to break, well, the start of my project was trying to break the record for the most dense bulk glass. So glass that is just made in a crucible, no fancy cooling techniques like a roller quench, just straight glass, and the highest density I've gotten is 8.66.
So that's about as dense as copper metal. So that's really dense. If you lifted it up, you'd feel this stuff is really heavy.
Yeah, like a 20-gram batch of that glass can fit pretty easily in your palm.
Yeah, it's a very, very cool glass. But we want other things as well. What we want, we're greedy. We want the Holy Grail, and Jamaica and Lord and others there. The Holy Grail is to be able to predict the properties of glass based on the atomic structure. Now, I told you before that a glass is a screwed up solid. It's cooled rapidly, and the atoms really don't form a pattern, um, which is true. But at the level of a couple of atoms, maybe 5 to 10 atoms, there's a lot of structural order. And we think that's that level, 5 or 10 atoms, that determines how the glass is going to behave in the world. So we want to understand what that structure is, make measurements of properties, and connect the two together, connect the structure and the properties together. And we've been doing that for a long time. One, for example, is the density, such as what Brandon just mentioned. A dense glass is basically how many grams per cubic centimeter you have. And that's directly related to the atomic structure and the atoms that are present. If you have lead and bismuth like he plays with, it's going to be dense.
And so part of my research that's going to happen over the summer is trying to use different machines we have, like Ramen. We're going to get an FTIR started up to figure out what kind of structure are in the glass that make it more dense and what kind of structures decrease the density. Because right now I've kind of just been making glasses and plotting the density versus the composition and other, like adding a different glass former, kind of changing it a little bit to see what happens. But ultimately, I'm trying to look at why it happens.
So I'm not sure if that's a new person, but it sounded like it might be.
I think someone left.
Or somebody left.
Yeah.
Okay. So, Rob, do you have a question? Just to give you the opportunity, we have Vani has asked and Lord has asked, and I'm not sure how many people are there at the present moment.
Yeah,
Oh.
I think Rick just left us, but hopefully they'll be back. Yes.
Okay. Yeah, we're looking at now. Okay. All right. Is Lord then there from Ghana still?
Yes, Laud is still here, and we also have Max. So yes, if you all have any more questions,
We
go ahead
definitely
and
have
drop
Max.
them.
Max is next to me.
Oh, that's the other Max. Max. Okay, sorry.
Yeah, we
Max,
have
let me.
two Maxes actually. This Max
Yes.
is our he's waiting for he's inviting you to send questions and messages.
Well, I do have a question here from Rob right now. Let me post it,
Oh,
and then
Rob, okay.
yes, and then I have a question. So this one is from Rob.
And then we'll put the glass into the furnace.
Ooh.
Rob, what kind of refraction indices do you get from these glasses?
We just got a refractometer.
We just got a device that
Oh.
measures that very property. So for everybody's benefit, the index of refraction is the measurement of how fast light travels on the average through the glass. So a number 2, for example, would mean, and the way the scale is set up, that the light travels at half the speed of light in vacuum. 3 means it travels 1/3 as fast as in vacuum. And so we just had a project, we're still working on it with a company in California on making glass as optically dense or to slow light down as diamond. Diamond really can slow light down a lot. The index is about 2.4 for Rob's benefit. So we go from normal glass, normal window glass type things, silicate glasses from which are about 1.5.
So just like look at your computer screen.
Yeah, index of about 1.5, which is slow down factor of about 2/3. Down to up to index of near can approach 3, which we light going about 1/3. On the lowest side, water has about index of refraction about 1.33 or so. So the range of indices of refractions for our glasses are about 1.5 to 2.4 or so. Rob, that's a good question. That's a wonderfully technical question.
For the glasses that I made, since mine are very dense, you end up getting pretty high optical densities. That's why in the project I ran some of my glasses to see if we would get close, and we kind of did.
You can see the Sam's camera, and that looks like Chris over there. He's mixing the glass now. We want a nice, well-mixed sample, so we make what we think we're making. Oh, we got a question, sorry. Hello, Vani. So Max has done his job. Thank you, Max. What do you think is fueling the increased need and uses for glass? Now, there's a question. These are all very good questions, people. Very good. It's an amazingly practical material. It's used in buildings, for example, and windows. You know, you can change how light, if light goes into the glass or is reflected by the glass by applying electric fields to it. You can actually change that property. That's a wonderful thing for windows. Auto glass is changing rapidly. You know, they're putting electronics into the automobile glass as well. Now you've seen heaters in glass. That's the old school now. But modern electronics require glasses that conduct electricity. That's why everyone is interested. Many people are interested in how glasses conduct, both ionically and electrically.
They also do other things like my antimicrobial glass. That's a thing that's happening.
We have a colleague,
Yeah.
Mario, who just stepped in for a second.
Your fiber optic cables, that's glass.
Fiber optics, definitely. So that's both for telecommunications and computers. Um, the new AI initiative, shall we say, that Google and other companies are worried about. One of our former glass students works for Google in Silicon Valley, and he has given us several lectures on the fact that they use glass in that process as well, um, in the use of optical fibers for the transmission of high-speed information. AI is coming, and that uses glass. So the volume of glass is increasing, as is the profit for companies. Corning, for example, is doing very well. You know, those flat screen TVs, that's a huge business for them. That is to say, the covers on your phones, that's glass, but also um, televisions.
Ah.
Those 50-inch screens, 60-inch screens,
If you've noticed the
which you can
glass
lift with
getting
the
thinner,
pinky now. They're so light almost. They're Those are amazingly technical glasses. They they are just a couple of millimeters thick, which is very, very thin, like something like the thickness of a piece of paper. And they're custom made with exactly the right composition. And then they're melted and put over a form, and they flow down the form right to the right shape. It's amazing. So Corning does that, but there are other glass companies in Asia
and
and in
also
Europe.
those glasses are very strong. If you've noticed the glass on your phone getting a lot thinner, it's because the glass has gotten a lot stronger, and so they're able to put thinner glasses on your
And
phones
that's
and on
true.
other appliances.
There's a reason they call that glass Gorilla Glass. They're so hard. Meanwhile, it looks like they've done the weighing of the chemicals. Oh Lord, I'm coming to you, Lord, for sure. I just want to make sure we get the glass into the furnace. So let me just go back to Chris over there and Zach, and tell me. So the Chris is the glass is mixed up. Earth to Chris.
Yes, yes. I'm sorry, the mute button did not want to go. So
Okay.
yeah, we after everything was weighed out, we cleaned our spatula again with acetone, and then we mixed for 5 minutes just to make sure that everything's well incorporated. And then we're gonna weigh it again by itself to see if there's any kind of difference or any sort of loss that we had during the mixing.
Sometimes glass sticks to the spoon. We worry
Especially,
about everything.
especially the boric acid.
Yeah. And the temperature of the furnace?
785 currently.
So we could actually probably put the glass in, but let's wait another 5 minutes. We'll give it a chance to get a little warmer, but it's already at a temperature where it'll melt the glass. So Lord asks, you were talking about the electrical properties of glass. This is useful in batteries, maybe capacitors and similar. Oh, yes. So the glass needs an electrolyte. I mean, the battery needs an electrolyte to control, to hold the voltage across the battery, basically, to control the flow of charge. And glass is one of the competing materials for the electrolyte. Sometimes you have this gunk inside of a battery. It's like a liquid electrolyte, kind of messy. and could actually burn your skin if you touch it because it's made out of some acids. The glass is not like that. Of course, you want the batteries to operate at higher temperatures sometimes. So the glass is pretty good about maintaining its integrity at higher temperatures. Um, Capacitors, for sure. We have a project with the Seton Hall University in New Jersey on making glass for this very thing, Lord, for putting glass inside capacitors for the making of ozone. What they're going to do is make microplasmas, as they're called. The plasmas are the little lightning bolts. If you apply enough voltage across the capacitor, a capacitor for everybody else is two metal plates basically with one positively charged, one negatively charged. If you ramp up that voltage, say to 5,000 volts, and you bring the plates very close, like 3 millimeters, and insert a glass in there, then you can create artificial plasmas, lightning bolts that go off, bang, 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 bang. Not, we can do that for at a later session, Chris. If he adds a little bit of copper oxide, the glass will turn blue, and we can show that. Now we have, I do believe it's Jamaica. Can you discuss the different type of glass used in spacecraft, satellites, etc.? Yes, so when you have a spacecraft, say going to the moon, which apparently we'll be going to more often now, that I believe is realistic. I would happen to disagree with Mr. Musk on going to Mars in the near future. We're not going to Mars, in my opinion, during my lifetime, because it's very, very expensive.
I mean, maybe not even mine.
Maybe not even, as Brandon just said, unless you're willing to make a few sacrifices. If you make that a one-way trip, then it becomes more possible. But let's not get into the gruesome details of a one-way trip to Mars. It's possible. The moon is possible. We can go to the moon. We went to the moon during my teenage years. I remember well. So for that, you do want glass to look out of the spacecraft. You want that glass to be dense. Real like Brandon's glass.
We
The,
love dense glass.
the reason for that is you want to block radiation from getting into the spacecraft. And space is not empty. It's filled with radiation hazards. Some coming from the sun, some coming from out of the solar system. There is radiation in space.
We actually have some of that glass here. We have a X-ray diffraction machine that blocks the X-rays using lead glass, so it won't damage us.
Lead-based glasses are very dense, and you can make them very clear so you can look through them. So that's a good question by Jamaica.
Can I have a follow-up to that? Because that would be amazing to see, maybe in a different session. Because I was just, of course, reading about the Lucy spacecraft flyby over the weekend of asteroid Donald Johanson, and I was very curious about the glass that's used in all the cameras that are used. It certainly can't be just things that are off the shelf. It has to be made specifically for the speed that things are moving, especially because there's all kinds of small micrometeoroids and things that could hit the glass. So it has to be strong. It has to withstand radiation. Is that a different kind of glass than what is used in like spacecraft in general?
So you want a thick glass to block that radiation, and you want, let's call it the Brendan glass. You want that leaded or other heavy metals to make up the bulk of that glass because that'll block the radiation. Now, it's a balancing act. You want to block nuclear radiation, but you want to let light through so you can see. So you can't make it too thick, or you're going to block a lot of the light, the visible light, I mean. Or you can look with infrared light, like the new James Webb Telescope. So the glass is customized, for each application. Those telescopes have glass. Another application, by the way. The James Webb Telescope has silica glass on it. The Hubble telescope is solid glass. Oh, 820, they're showing me the temperature. And I think, you know what? I want them to see the glass itself. So guys, show them, go ahead and put the glass in. Oh, and we have another question from Lord, which we'll discuss momentarily. In the meantime, let's watch Chris and with Zach, put the glass in the crucible. And once we make this glass, we're going to save it because it's 4:41 now here, and we'll do the thermal measurement. Well, I'm not sure we'll get to it today, but we will get to the glass for sure.
Also, if you notice what they're wearing, they have uh, gloves that are pretty thick that'll protect you from the heat. They are holding the crucible with some tongs, and they have eye protection. So
Get closer to the furnace and show it again, guys. I want them to see that wonderful heat. Oh yeah, that red is the glow of the furnace. Yeah, close it for now. And now, Zach, I'm going to answer Lord's question now. But Zach's walking away. Chris, can you hear me? There he is. In about a minute, no more than about a minute, I want you to open the furnace door, take the crucible out, which we don't normally do, so you can see the water coming out. You can see the evolution of the water in about a minute or so. So he'll get ready for that. And Sam, go ahead and video it, even though I'll be talking for a second here. Don't worry. I'll demur. I'll be quiet. Lord, thank you. How different is the process for making glasses for optical applications like terrestrial telescopes, small and large? Wow. Another good question. I've seen them made. I've seen the big telescopes made. What they do, the process is a little different. They spin the glass. Under the football field, one of the main places they do this, under the football field at the University of Arizona in Tucson, they spin the glass hot, like at the temperature this furnace is at now. And the glass will move due to centripetal forces, it'll move up into like a parabola, like a bowl shape, which is exactly what you need for a mirror. So they actually spin cast the mirror blanks. Now the James Webb telescope had, I think it was 9 pieces to the mirror, or something like that. It was so big they couldn't do it in one step. So the best telescopes are coated with like gold in the shape of a bowl of a parabola. The reason for that is that the light is then all focused at in the middle of the telescope to capture as much light as you can. Okay. Meanwhile, what just happened?
should we see now?
He's signaling that he's getting ready. He's putting the glasses on. There's Zach. Ask more questions in the meantime, everybody. Feel free.
I
And
have
Zach,
a question.
go ahead.
Zach he picked up, there's like a blue implement on the table. He used it a minute ago, but I couldn't quite see what it was. What is that?
It's an infrared thermometer. We use them for just for a safety sake. A lot of this is safety. Unless you have something like the furnace where it's red hot, you generally can't tell 500 from 0. And so we use that to make sure we don't like cauterize our fingerprints.
Oh,
Yeah.
right. That's good.
That's a good mental image.
Yep.
Okay, it looks like Chris is going to have the honor this time of taking out the sample. All I want, Chris, now, go ahead and take it out, is to look at the steam coming out. So hold it in the tongs, bring it out, close the door so the furnace gets warm, close the door, and bring the camera up close. Close, 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 close. You see it bubbling there?
Oh, wow.
And I can see some of the steam coming off too.
Yeah.
Those bubbles are coming from the water being pushed out of the glass. So that's making like a very thin glass shaped by the water vapor. Now I was going back in And in about 5 or 10 minutes, we'll take it out again, and it'll collapse. More water will come out, and the glass will collapse to the bottom of the crucible, and we should be able to see the glass.
This is why making sure you melt your samples for the appropriate amount of time is so important. Because imagine if we melted this for 5 minutes and all the water didn't get out, we'd have a sample that would be kind of inaccurate.
You're correct. The water would still be in there.
Yeah.
So anyway, if Sam can get closer, we can look at the temperature of the furnace. And it's a little bit lower because we opened the door of the furnace, but it's going back up again fairly quickly. You see that? 808, 809 in a second. There you go, 810. And so it's trying to go to 1,000. I'm going to, for the purposes of the demonstration, I'm going to ask Zach or Chris to raise the temperature to like 1050 to speed up the heating a little bit. Can you raise? Yeah, there you go. So,
Also-
and you guys can watch. There's a controller. He's increasing the temperature of the furnace to about 1050.
Also, fun fact, you can program these. So these furnaces cost, how much do they cost? Like 1,000, 5,000?
This particular one is about 10,000.
Yeah, so it comes with a program control with about 8 different programs. You can set it to rise to a specific temperature over a set amount of time, immediately jump through a specific temperature as fast as possible, cool down slowly through a temperature, hold on a temperature for a little bit. So you can make pretty intricate cooling programs with this, and this can help you reduce stress on the glass, which will help it crack less. Or if you're trying to get it to have like a specific form, you can manipulate the cooling so that it's easier to achieve that.
So I see Zach is by the what's called differential scanning calorimeter, the device that heats the glass up, so we can measure the softening temperature. Sometimes the glass can crystallize, and we can see that temperature. Sometimes it melts the crystal that forms afterwards a glass. We can measure that temperature. And now that you're there, Zach, maybe you can call up a typical run. Can you do that? I think he can, and he's going, and then we're gonna get Sam to get close in so that we can look at what the experiment yields. This was done a few days ago, maybe, or a few weeks ago. Because Zach is doing active research with this, he can choose, from his own research effort. All right. So just a typical run, okay? Okay. So getting closer, Sam. So you can see that the x-axis there is temperature. Zoom in on that. There you go, temperature. The y-axis is basically heat in or out of the sample. Okay. And this actually measures a few things. It measures heat in and out of the sample. It also measures the weight of the sample as the sample is heating up. And you can see that it's a straight line, but then it flattens out. Can you see? Yeah, zoom in on that. It flattens out where the glass softens. And then there's a huge peak going up. That peak that goes up is the glass becoming a crystal and kicking out energy. And then after that, let's see, it comes down a little bit. Yeah, that going down is the melting of something. And there's a big melting. Yeah, right there. That's melting. So this instrument is extremely sensitive. Okay. So we're going to do that same experiment on this glass as the teaser, I guess, in the next Shadow of the Scientist session.
Yeah.
Meantime, guys, feel free to ask questions. I'm not sure who's there at the moment. How many people are there?
Okay, Laud has another question. Let me go ahead and post it. And then I have another one as well. And then we have another one from Vonnie also.
Okay. Lord. Oh, so I explained that, for the large telescope, you want a mirror, which is then coated with a metal. So that one I talked about.
Yeah.
For small telescopes, they would make the lens, that's interesting. There are a few ways they would polish the lens actually to the correct shape. Of course, they would polish the big one too. Oh, those are the inner guts. That's the inner guts of the differential scanning calorimeter. And there's a little sample pan in there, which is ready. There's a ceramic dish in there, ready to take a little bit of the glass that's heating up right now.
How much
So
does this machine cost, Doc?
this is not a cheap instrument. This toy over here is $270,000.
Eesh.
So we got this toy that Zach, undergraduate Zach, uses. We trust him.
Coe makes it
But
possible.
he's done a few very good things. Once he dropped something near it, he called me immediately on a Saturday. What do I do? We discussed it. He then turned off the machine, and then he was able to recover it on Monday. It all worked out. It all he actually found what he had dropped. There was no problem in the end. But he did the right thing. Okay. Vani, what material is the crucible made of that contains the glass in the furnace? Right now, Avani, it's pure platinum. By pure, I mean over 99% platinum. You'll be surprised that platinum can withstand very high temperatures. It doesn't melt until over 1700 degrees Celsius, which is like, oh, I don't know, almost 3500 degrees Fahrenheit. Very high temperatures. And it also doesn't react with the glassy material.
There's
So,
also other crucibles, like I've used alumina crucibles, which don't go as high and are generally one use because they crack. There's ceramic crucibles that are a lot cheaper, but still serve a purpose. There's graphite crucibles. There's platinum gold alloy crucibles. Doc's used a lot of them. He's used more than me.
I'm older than them.
Yeah.
So how's the furnace? We'll get Sam over there, and let me thank Sam. There's Sam and Chris and Zach over there. We have Max and Brandon over here. And do we have a Max in there too, Zach?
Nope.
Okay. Okay. So go to the furnace now. We have about 20 furnaces in total. Temperature is 868. And I'm watching the clock. We will end around 5. I want some more time for questions. Here's Vani. How did you first become interested in making glass and why? What about the students? We'll get to this question. It's another good question, and I will get to that. But I wanted to take a look at the sample so that you get to see the glass. But I will maybe we'll go to 5 after 5 then, so we could discuss this. Okay, Vani?
Is
I'm
it
gonna
break
answer
lunch
it.
time?
I don't think I think it's gonna be look in the crucible time.
Okay.
So go ahead and take the sample out, and Sam, get that camera ready so that we can look directly into the crucible, but don't touch anything, Sam. It's going to be rather warm. Temperature in there is about 16 to 1700, maybe 1800 Fahrenheit.
Yeah.
Doc,
We
do you want to see
only
Lake Munch?
You think it'll come out? Maybe. Um, we can try it. Let's be optimistic that we can get the glass out. Now, normally what we would do is weigh it, put it back in the furnace, heat it up again, and then pour it. But we'll skip the second weighing right now. Let's see if we can actually pour it out. So there's the sample coming out. And turn over that crucible quickly. Turn it over. Here we go. Let's see if we get it. Did it come out? Plate down. Okay, just hold it. Looks like it worked. I saw the glass come out. Did you see it, Zach?
We got a little bead.
I think you got some. He's putting down the crucible on, that's graphite, I think. And let's look at the crucible. In fact, before we look at the sample, Zach or somebody lift up the crucible, get Sam to get that camera looking into the crucible, and let's take a look at the glass itself in the crucible. In the crucible. In the crucible. Use the tongs. Tongs. There we go. Hold it up to the camera. Close, 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 close. Yeah, there's the glass. You see it shining the light off of it?
Oh, wow. Yes.
It formed glass. Nice clear glass. And so I'd say cool, but it's hot actually. That's hot.
You also can't get too close because at this heat, it can shatter the camera glass.
Yes, it could actually explode. Hence they have glasses on and gloves. Uh, Now, if you lift up the plates are stainless steel, and get in close. Oh yeah,
Ooh.
some beads of glass. You see it there, Jamaica?
Yes. Wow.
Now, what I'm going to ask the guys to do there, and then I'm going to answer Vani's question. Vani, your question's a good one. Um, Gather that glass and put it into a sample tube so that we can do experiments on it later, okay? So they know what to do. They're good at it. And then Sam or somebody lower the temperature of the furnace back to about 200. We always keep the furnace on, but at a lower temperature. All right, so we're saving the glass, and then we want to label it, and put it in a good place. Okay, that's good.
Do we
So
box this one?
we can. It's this particular glass that we chose is a pretty stable one. Oh yeah, take a look in there. You can see the glass pieces.
Is the glass still hot? I noticed that was still using another implement to move it from the stainless steel plates into the sample container.
It's probably not very hot, but that's a safety consideration.
Doesn't the plate punch cool it? What's the rate like?
Well, the plates cool it at about 1,000 degrees a second.
Yeah.
So after 1 second, it's almost at room temperature already. In fact, they're going to try to measure the temperature. It's going to be room temperature pretty much. Okay, now, Vani. So to be honest, when I was a physics major my whole life, I went to one of the science high schools in New York City. Then I was a physics major in college. I was a physics major in graduate school, physics professor. Then so physics. Um, in graduate school, I went to Brown University, and one of the world's experts on the structure of glass was there. I went around as did other graduate students to make a connection to join a group, and that group seemed to fit my needs at least, which was a friendly group, an approachable professor, approachable fellow graduate students. I didn't know anything about the structure of glass at that point, just that it seemed interesting. And then it's like an onion, Vani. You peel back the onion, and the more and more layers of knowledge of it keeps giving. It's the gift that keeps giving. Now, Max hasn't done much yet on glass. He's a first year, right? But Brandon's a second year guy, and Zach is second year, and Chris is second year. So one or more of those guys can answer the rest of Vani's question.
Yeah. For me, it's a very lucrative field. I didn't grow up the richest person, and so finding a career option that was both interesting to me and could lift me out of poverty was very important when I got to college. And getting in, that's why I chose STEM. It was one of the big reasons because I was interested. I did calculus and chemistry in high school. I got here, started making glass, was like, I don't hate this. Did it more, and I was like, I actually kind of like this. And
I like how
now,
you describe it.
now Doc tells me, hey, Brandon, I need you to slow down. Stop making glass on the weekends. And I tell him,
Sometimes we we have a little debate. I say to him, "Go to the movies once in a while. It's okay. You're allowed to go to the movies on the weekend."
I did watch a movie while making glass.
I admire his drive, though. Usually, I'm the other way, Jamaica. I mean, students sometimes need a little encouragement.
Mhm.
And I'm all for people doing research and studying. All that is good. But this young Brandon over here can go 10 to 20 hours at a time. Sometimes take a little break, take a nap once in a while. Um, it's a very rewarding area because it yields results. It might take a year or two to get a project really well along, but I don't know, Zach. Maybe Zach can show you some of his softening temperature measurements if it's easy to get at. Oh, so they're in the glove box now. They put the sample in the glove box just to store it. Then it's going on the shelf, so we can use that glass and measure its softening temperature. We're going to do that, not at 5:01 p.m., but we're going to do that.
Hey, the day is young.
Yeah, it is young, especially for Brandon. So they're the guys. Um,
Steve, do I have the right understanding that all of the students working with you are undergrad students?
that's the right understanding. Coe College is an undergraduate institution. Now, one of the secrets of what we do is we start them off early. By early, I mean we invite students to join us the summer before they matriculate, before they take a single class. They join older students in research.
I was here for 2 weeks the summer before. So was Zach. I think Chris was
For-
offered, but he just like forgot.
So, but even that first year, we like to get people involved. And that first summer is very important. We don't wait until they're juniors or seniors. Multiple years mean so they'll have projects like in the case of Zach, he's been studying germanate classes. Germanates are like silicates. They're a little further down the periodic table. They're like heavy silicates. Whoops, something's happening here. Young Brandon is.
Yeah.
Okay, we're back where we can see everybody. Um, did that answer your question? I can't remember if I answered all parts of it.
Yes, no, it does. I think that's fascinating that the students, even before they get started with their first classes, are
Yes.
introduced to the faculty and they can actually interact with older students and see the types of research that's possible for them to get into. And the equipment that we got to see you all using is it seems to be really special that undergraduate students are trusted to be able to use
That is a special thing